how to analyze this massive amount of single particle trajectories. I present you the theory of some of it, and we'll do then the exercises. So the idea is that this is the exponential, or let's say approximated exponential curve of how the number of paper in single particle tracking has been exploded over the last 10 years. I'm interested in this. So you have many trajectories on the surface of the neuron and the membrane. So there are two ways to analyze single particle trajectories. One associated to each trajectories, and the other where you combine them. So single trajectory, you can do segmentation, that is from the left. How do you go from the right to isolate, for example, the position where the particle or in the trajectory you have confined versus unconfined. So this we develop. This is not the goal of the presentation, so I'll go very fast, but just for you to understand that there are two ways. So you can calculate diffusion, anomalous diffusion, and you can calculate the switching rates. You can calculate any statistics of interest, and there are many ways to do it. We develop tools using 4 parameters, so you can classify in 4-dimensional space using machine learning. If you're interested, it's not in here. The plugin exists. You just have to download it. So this is one. Yeah, you go to Imaj, Fiji Imaj, and you go to plugin, you go down, and you go SPTanalysis. But now it's just a general presentation. Today I'll discuss how do you combine many trajectories, not because ultimately, why are you interested in a single trajectory at a time? It's to get statistics of the trajectory, the one thing, but if you want to get more into the underlying structure, you need this combination, as we'll see. So you can go and use this to get information about high density domain, phase separated domain, or even secondary structure at a nanometer level to extract, for example, from the ensemble of trajectory, if they are path, if they are flow, that you cannot see from single trajectory, you can only see it by combining them. Okay, so basically in the last 10 years, we've been looking at this for on-pair receptor, where you see the high density, the spot here for high density region, and it is associated to a structure which we call potential well that I'll describe. I don't find it, you don't see the pointer somewhere, no? There, over there in the box, you have in the back behind you. Do you see a pointer? Yeah, that will be easier. Yeah, good. So you see this spot here, it corresponds to high density region, and associated to this, you have this potential rate, this structure I will describe. So you can do this for calcium voltage channel, and you see associated to calcium transient, where you have high calcium, you can see that this area corresponds to region you have accumulation of receptors, and they're associated to a structure that maintains them, which is a potential well. By looking at trajectories of lysosomes, so if you've been yesterday to the lecture of Lippincott-Schwartz, you can get from this lysosome, this is how we discovered that they are following so well the ER, because when we found this, so it has to do with some kind of network structure. And it led to a study where indeed we show that this is very highly correlated. So again, you can use single particle trajectory to infer underlying structures under which this trajectory show that the vesicle or lysosome were trafficking. And from this, you can even reconstruct, and this will be the second part of this presentation, you can reconstruct the graph associated. In neuromuscular junction, you can see how well are organized this structure, high density structure, these potential wells. You can use this, we will see how to, from single particle trajectory inside the endoplasmic reticulum, each color corresponds to a trajectory associated to one color, but as we will see, if you change the color code, if you start to plot the velocity with a color code that high velocity is red and low velocity is blue, suddenly you start to see the topological organization emerging from trajectory. And you can use this for viral protein aggregation. This is what we did more than 10 years ago, where from GAG protein, you could see that we found out that the aggregation was again associated to a transient potential well. Okay, so basically you have a large amount of single particle trajectories, and you want to do automatically, you don't want to anymore to write any codes. You want to detect from all this diversity the region where you have high density, and you want to characterize them. And as well, you want to have information about the diffusion property at each point, the density and so on. Okay, so that's the goal of the software and plugin that we have developed. You start collecting your data. You use any single particle tracking algorithm that will link the point to get the trajectories. And then we start. You can take your image, you can discretize the environment, and explain the underlying biophysical model. And from this, you can, from this ensemble of trajectory, create the density map, the drift map, the diffusion map, the displacement. And automatically, I'll explain to you how from this you can detect the region of high density and find a boundary, which is the hardest part, where you have to position, where is position this abstract boundary. So there are algorithms based on minimization procedure, and you can use also this to reconstruct nodes or region of density in graph. And then the output give you the possibility to extract files, CS file, where you can get all your statistics of interest, the parameters such as the dimension of the ellipses associated to this structure, the energy, mean time, and so on. Okay, so this is what the pipeline is doing. All right, so this is what I've shown you already, the fact that you can have this restricted region where you have this high density, and you want automatically to generate these round circles or these ellipses. So again, you have trajectories. From the trajectories, you can get the density map. You can extract the diffusion map. I'll explain how this is done. And you can extract the drift map, that is, what is the resulting direction when you average all your trajectories at a specific location. So what to extract from single particle trajectory? So for this, we need a model. This is the first thing. Otherwise, it's not clear what you are doing. So we started from 300 years ago with Newton's law of motion. Force is acceleration. Then Langevin said, it's not enough to describe motion in the fluid. You need to incorporate the friction and the Brownian motion. And then Smoluchowski later said, yeah, but if the friction is sufficiently large, you don't care about acceleration. So you have the friction plus force equal diffusion coefficient. So if there are no forces, the resulting behavior is associated to diffusion. So that's vision prevailed up to now, and it's sufficient to characterize many of the systems where we have this single particle trajectory. Why this is interesting? Because it's a trajectory. The result of this equation is the characterization of a path of a trajectory. So now you ask the question, if you have many trajectories, or trajectories in general, you want to find the force and you want to find the diffusion coefficient. So you have to do a reverse engineering problem. And it has been solved 70 years ago, not in this context. And the solution goes like this. You start with the equation and you discretize between t and t plus delta t. So you multiply everything here by delta t. So the displacement is force plus diffusion term. And what has been found out is that if you average this quantity for a point in a given, for x of t at a given point, you divide by delta t and you average over all the realization, which means all trajectories, you solve this equation exactly. So that was the starting point 10 years ago of our approach. How do you implement it? It's very easy. You have an image, you cut it into square, so you make a grid, and at each point of the grid, you look at when x of t falls into this, and you look at xt plus delta t, where is the next point? And this will give you a vector. From the vector, you average the vectors, And this will give you the resulting force at a given point. Of course. Yeah, you assume that you do, for example, palm, or you tag your receptor. You assume that you have the one type of receptor, of course. Otherwise, if you have two different types, you have to do different labeling, two different colors, and then you can have a mix, but you know what you are averaging. You should not average things that are not the same.
And the criteria are they passed in the pixel or are arbitrary?
Arbitrary. And you will see, you will play with this parameter. You can have it small or large, which means few, let's say, nanometer to 20, 50 nanometer. And we will see if you have a large one, you lose in resolution. But if you are too small, you may not have enough point that falls into this. So there is usually an optimal. Okay. Okay, so you do the averaging and it is a drift. You do the averaging square, this is diffusion coefficient. And that's it. That's the theory. And then what we've been is improving in that direction. So instead of, if you want to improve, you can take a ball, all trajectory falling into this ball, and now you can move the disk with a resolution which is much smaller than the grid themselves. And you look at point falling into this, you multiply the point by a weight function, cosine function. And if you do this, you can calculate drift and diffusion coefficient, and this is the result. That's an image with trajectories. This is the raw image, and this is the one with the smoothing. So you see here the pixelization, not great. And you see here the effect of the cosine filtering is give you something much more, much smoother. Okay, so now let's move on to the characterization. Now we've seen this is a general characterization. You have all of this trajectory, you apply this. Now, suppose you have a region where you have a large amount of trajectories. How do you extract the features and what features to extract? Trajectories are here. You can look at just the density. You look at how, just look at the points, and then you can calculate the drift the way I explained to you. And interestingly, if you have long-range interaction, they are characterized by converging arrows. Now, this is something interesting. If you have such a signature, now let's discuss what's the theory behind. So basically, if you have a field of force, and if it's a conservative field of force, the force will be the gradient of a potential. And generically, if you have a potential well, it is characterized by a parabola, and if the diffusion constant is a constant, then the local density associated to this drift plus the effect of diffusion is a Gaussian. Is a Gaussian characterized by, at first order, just this parabolic term, where we have a finite number of unknown parameters, which are the center and the coefficient A of B of the ellipse of the disk, and this coefficient A that characterizes the energy. This is classical chemistry. You have your potential well, it is truncated. It can be more subtle, you know. This is really the basic stuff. You can have something more smoother here. But let's go with this very general structure. This is what you have seen 2D. And if you take the gradient of this, you have the signature of a converging arrows. So this is a signature you would like to find in your data. Again, with the idea that you will extract the center size energy, which are 5 parameters. Okay, so this is summary. You are interested in finding it. Now it becomes a mathematical problem in estimation. What are the parameters, the center, A and B, and this capital A? So this is the equation. I don't enter into these details, but that's what you are looking at. You look at B and A, which are the ellipses, small and large axis. The energy is capital A. It's A divided by D, actually. So if you know the diffusion coefficient, which you can get because you look at second order property, then you can get all the information of interest that would characterize the energy of the interaction between your well and your receptor or the quantity of interest. And you can even from this infer the stability by calculating what is called the escape time. That is, in average, how long it takes for a trajectory to escape. So let me repeat this. you have many trajectories. From these trajectories, you cannot calculate the escape time, because for this, you need to reconstruct the boundary. Once you have the boundary and you know the properties, you can use this to get information about the stability of your structure by calculating quantity that you could not just calculate with just the trajectories. Okay, so those are examples of the last 10 years. You look at, for example, dendrite, you look at the region ABC of high density. You use the algorithm to define here this potential well, and we have even a quantity that measure how good is your reconstruction, how likely is your potential well, so you can quantify, give a number for all this structure. And a couple of years after, this has been repeated by different groups to prove that indeed potential wells were there, and this was not something we just invented. It depends. What do you mean? If you want to, if for example the immobilization is resulting from a potential well, you will detect it. If it's just the fact that the molecule doesn't move at all, you will detect it, because you will have, I mean, if in trajectories, I mean, it should move at least a little bit, then you will identify this, this structure. It should be, yeah, we have, I will discuss, we have a multi-scale aspect of this. It will come when we will play with the software. So again, this was what I showed you before. This is a calcium transient. Associated to the calcium transient, you have aggregation of receptors, and associated to this aggregation, you have the structure of stabilization. This was important to better understand what happened in presynaptic transmission. How long calcium voltage channel can stay near vesicles inside these nanodomains. Okay, so now I will spend 5 more minutes on the algorithm, and then we will start. And then once we do the first part, I'll go to the second part about the reconstruction of graph and network structure. So what are the algorithms that you're going to look at? The algorithms are based on looking at the density of points, at the drift map, and an hybrid. And then we did a hybrid algorithm that combined the two. So this allows to extract the lengths A and B, the center mu. And from this, we can again apply this algorithm to extract the field of force, which give you the energy. And with the local estimator, in parallel to this, you get the diffusion coefficient, so that A divided by D give you the information about the energy. So basically, how you recover the center, you take the trajectory and you just take the average. That's easy. This will give you the center here. You can use the covariant matrix, which once you have the center, you calculate for each point the difference with the center, you do it square. And this covariant matrix allows you to get information about the steady state density, because in the model, it's just a Gaussian as an approximation. And so now the extraction, you have to extract these parameter lambda x and lambda y. And for this, you use this diagonalization of this covariant matrix here, C, where the density is centered at the center mu with a variance, this covariant matrix. And what is interesting, when you have enough trajectories, you can see that actually this quantity, C11 and C22, are converging towards this axis length, A and B. And the ratio is important. You can calculate A over B. And this is relevant when you want to calculate the estimate when you have an ellipse. Okay, so the density algorithm uses what is called the level set. That is, you look at the maximum, and from the maximum, you can sample where are the points where you have, let's say, a certain proportion of the maximum, let's say 40%. And then you see from 40%, you can extract some information about where could be your boundary. And if you have trajectories that are generated inside, this is just when you have trajectory inside the well. And if you have trajectory that goes outside the well, you start to see the idea that there is a gap between the inside the well and outside the well. And this is this gap that you would like to capture. Okay, so I'm not going to discuss this. So I just give you an example of how you can determine a circular boundary. That is, you look at what happened between R and R plus dr when you know the center. And when you do this and you expand this R, and for each R you calculate this radius, at some point you will have a discontinuity, and this is this point that the algorithm is looking for, and this will be an estimation of your boundary. So the algorithm is first determine the center, compute the ring between R and R plus dr, and look at the inflection point, which give you an approximation of the boundary. This is algorithm number one. So yeah, I don't want to discuss this in case where you have an ellipse. It's a little bit more subtle because you have to do a renormalization, and I don't want to go into this detail because what you have in one direction is not what you have in the second one. So it becomes more subtle to extract the two coefficients, because you see, when at some point you arrive to here, the next circle that you're going to use is not going to work. So you have to renormalize, but this you know because you can calculate, as I explained to you, the ratio. But let's not enter into this point. Okay, this is too much mathematics. I just give you the flavor of the boundary extracted from the drift. Suppose you have a drift, which is an ensemble of converging arrows. Everything is converging here. Where are you going to find the boundary? Where? Well, if outside this ensemble of converging arrows, you suppose that you have Brownian motion, then the drift should go in all directions. And so what you are interested in is to extract the region where you will get here diverging arrows. And so this is what you do. You look at how the drift increase with the radius, and at some point you'll see some fluctuation. And so this is exactly the point, the distance that you would like to extract. Okay, that's the principle, the idea of how it works. I wanted, before doing all these exercises on Imaj, I think it was important to explain to you what are the essence of those algorithms, where things are coming from. Okay, so again, I'm not going to show you all of this math. There's a maximum likelihood estimator, which is basically given the data inside your domain, how you calculate, how you estimate the center, the diffusion, and the energy. So there are formulas to do this. It's a classical maximum likelihood estimator. Again, no point of discussing all of this there, but just to say that you have the formulas, and we implemented those formulas. And the difficulty is where are the points? Because for this, it assumes that you know the boundary. So you should only use this once you know the boundary, because you know where are the points that you're interested in. They are outside. You don't want to put your statistics outside into what is inside. Okay, so basically we'll have three algorithms: the density estimator algorithm, least square estimator based on the drift, as I explained to you. There's a maximum likelihood estimator once you know the boundary, how you calculate A, D, and other parameters. And that's the three methods that we're going to discuss. Okay, the rest, I don't want to discuss all the algorithm in detail. So I think just to summarize, trajectories, you go to density, you have the drift and the level lines. This you apply an algorithm that will increase, given the box, the different ellipses that you can fix the size. Once you have all of the different ellipses, you have to fix a moment where you stop. And then you go back to all your ellipses, you calculate here the density, you'll find the inflection point. You look at the least square comparison, we have a criteria, so you look at the local minimum, and the maximum likelihood, you look at this local maximum. Okay, so this is an example of what you're going to do. You are going to get the trajectories, you will see the drift, you will see the visualization how we calculate the potential. Those are examples from calcium voltage channels with long tail, short tail, and then you can do the statistics over hundreds of these structures. And the last thing I wanted to say is that you can do a time-lapse analysis, which says take your data between 0 and 10 seconds, 10 seconds, 20 seconds, and so on, and then apply your algorithm to look at how the structure can be reconstructed from independent trajectories. That's very interesting because it means that you don't have correlation, at least not in time. So then you get all of these potential well reconstructed, and there are moments of time where there is no potential well, and it disappears, and it can reappear again. And so by this, collecting all the frame where you have those potential wells that could have varied a little bit, so you have to accept that there are potential variation between these. This is all the ellipses that you see here, and all the ones that are there. And then you can estimate the stability of your structure over time. And this will give you an estimate of the stability of these nanodomains. And we did that for calcium voltage channels, ampere receptors, and so on. So this gives you an additional information about these structures. Okay, so I'll stop here. And now we were going to work all together on this software that does all of this. So now I'm going to stop sharing. There is no notion of equilibrium on this analysis. There's no equilibrium because when you acquire this trajectory, you acquire them for a certain transient time, and there are different moments. So you are capturing the most likely event at a given moment of time. And by doing this, you reveal this structure. So there is no equilibrium that you should have in mind when looking at single particle trajectories. I mean, the art equilibrium. I mean, okay. What is the meaning of equilibrium? It means that trajectory, for example, if you have Brownian motion, if you have two particles and you have an ensemble where they are supposed to be equilibrated, they are moving. And now I look at a given window. Sometimes I see nothing. So what is the meaning of I see nothing and still I'm at equilibrium? Now, if you have hundreds of thousands of particles and I get a window, and then I see all these particles, and at the population level, you'll see the number of molecules will not change much. You'll have some fluctuations. The stochastic approach reveals this non-equilibrium aspect of the system. The fact that you can have small amount of molecules, that they are in a transient situation, that's what it reveals. And then you'll have to do your statistics, and I'll show you when Pierre will give you the example of the analysis of what happened in time in the ER. We'll see that over a long time period, if you look at the number of trajectories that went in and out from a well are equals. They're equals. It doesn't mean that you don't have this potential well. You can have this potential well and still be at equilibrium. Okay. Okay, now I'll leave you with Pierre.
Yes. Yeah, I'm here.
I should stop sharing. No,
I'm sharing now.
So if you are sharing, why? Wait 1 second. So because we don't see your screen. Yesterday, wait.
Yeah, yesterday it worked.
It worked very well. Wait, let me just 1 second stop this. All right. So why don't you share? And I will put it in here. Yeah. Okay.
Okay.
Yes, go ahead, Pierre.
Okay. So do everybody has the subject and everything?
Yeah, you have everything, right? If you go to, we can start, I think the SPT has been installed, so everybody has the SPTanalysis. SPTanalysis, so you have SPTanalysis. Yeah, okay. Yeah, okay, good. So you have it? SPTanalysis? SPTanalysis. Okay, yeah. Yeah.
Okay. It's okay?
Yeah.
Yes.
Like this is okay? Okay, go ahead.
Okay, I'm just going to very quickly show you how to install the thing in case. So in the practical subject, you have links towards the things you need. So there's only two things basically. There's the plugin, and there's another jar file that needs to be downloaded. So this is the plugin SPTanalysis, and this is GTS. It's just another thing we need. So simply take these two things and put them in Fiji in the jars folder, and that's it. Now, when you launch Fiji, you should get in the plugin menu at the bottom this SPTanalysis. All right, so if you have the version from yesterday, we will have a very slightly different version. I just corrected some bugs that I found yesterday, but yeah, more or less it will be the same. So this is for the plugin. Now the data, here we provide the 3 data sets. This data set 1 are voltage gated calcium channels in hippocampal neurons. Data set 2 is luminal ER luminal trajectories, and data set 3 is similar voltage gated calcium channels, but at the drosophila neuromuscular junction this time. All right, now we have the data here. So the first thing is, this is the first window that you get, right? The input window. So there are 3 options to load files. Either you can load file in plugin format. So this is something we will discuss after, right? It's something file format you can save from the plugin. Or you can directly load files from TrackMate, or you can load file in custom format. For example, we can start with custom format. So custom format means you have 1 spot per line of the file, and the different columns will tell you different information. So for this, you have a bunch of options. So what is the delimiter of the file? Where can I find the column that corresponds to the trajectory ID? Where can I find the column that corresponds to time, to X coordinate, Y coordinate? And then you have extra options, right? Like, for example, if your trajectory have a Z coordinate, you can specify it. And this last bunch of options, if you want to skip lines from the beginning of your file, and if you want to specify the pixel size, if the unit in the file is given in pixel, and same thing for the acquisition type, if the unit is given in pixel. So if we look at the first data set, which is the voltage gated calcium channels, and we just open the file with a text editor, right? We see that the first 3 lines of the file are actually not data, but they are just information. They are headers. So we are going to skip them. So in the input, right, we would say skip header lines, skip the first 3 lines. And then what we see also is that here, this information, the position of the spots here in X and Y, it's given in pixels. So our unit is actually pixels, so we need to check unit is pixel, and we need to find the pixel size, and the pixel size is actually given in the file here, and it corresponds to. Yeah. Sorry, it's not the file, whatever. These files have the same format, right? But it just. Okay. So our pixel size is 0.1 micrometer, so we can write it here. And the acquisition time, same thing, is 0.0. Right, so skip header length 3, unit is pixel check, pixel size 0.1, unit is frame check, acquisition time 0.02, and all the other parameters, they are already correct. Then now one thing we need to determine right now is whether or not we want to use time windows. So if we want to cut our file into different windows, as David started to present, right, with the wires, if you want to evaluate stability and things like that. And this, we need to do that now, and we cannot change it afterwards. So let's just tick it, and let's just use the default, so 20 seconds time windows, and 0 overlap between them. Right, then I choose my file, which is the dataset 1, and I load. And if you specified everything correctly, you will have the main menu that appears. If you did something wrong, you will have an error, and you just need to correct the format. So in the plugin, right, you have the main window here, which is called SPTanalysis, and you have the visualization window here. This visualization window is just Imaj window, right? So you can zoom in, out, you can move the window, and you can swap between change time window by scrolling with your mouse, like you would do with a normal image window. And one thing that's important to see is that you specify the correct information. So if you click on the first button, right, in the main interface, the info button, you will get information about your trajectories.
Yeah, 1 second.
Yeah.
Yeah, okay. So we are at custom. Just click on use time windows here, and we put skip line 3, and here 3, 0.2. You click here, and then time limit 0.1. You click here, and 0.1. Okay, so once you do this, good, and you choose the file and set load. Good. So
the file we stored, file.
Yeah, so this is the file. Which file you are here? What is the file?
The file is 180321 C21 intra EOS 32 blah blah blah.
Okay, I think we're good. All right.
Okay, so just something that's important is to check that the info you specified for the pixel size and acquisition time are good, right? So you go to the info menu and just acquisition setup you need to make sure that these things are correct because they influence, right, all the things you will get down the line.
Okay, very good. And now you get info and you get information. So everybody has info? Yeah. Okay, we are at info.
Okay. So the thing we can do now, right, is just to make our life easier, is to save this loaded file as a plugin format. So just click on Save Plugin and just specify a file name, right? For example, toto.xml. And now we have saved the file as a plugin format, and we can just load it directly. For the moment, it's not super useful, but then when you will do analysis, like well detection or graph reconstruction, the plugin format will also save this analysis, so then you can retrieve them later.
You will see, we can export a lot of things. Okay.
All right, I just want to show you the loading of the other file. So if now we just close all of it and reopen the plugin, so SPTanalysis, and now we choose TrackMate. Now we have much less options. So we can directly specify the dataset 2. So this dataset 2 is 293T OG2 spots in track statistics. And here we just have to determine if we want to use time windows or not. Let's say, okay, yeah, we want to use time window, same thing. And now we can just press load directly. So loading TrackMate files is very easy. And here you noted that we did not specify acquisition time or pixel size or whatever. But actually, if we go in the info, we will see that we have an acquisition time that has been computed from the trajectories directly. We don't know the pixel size because it's not specified, but we determine the acquisition time, which is 18 milliseconds.
So wait, everybody has this picture? No. So wait. So it's 299, 293.
Yeah, it's this 293T OG2.
Yeah, and we are in custom, right?
What, sorry?
What is the load from custom?
No, it's TrackMate.
TrackMate. Okay, you go to TrackMate here. TrackMate. Right, you click on use window, click on this here, and now you go. Okay, good. You have it.
All right, now we can also save it as a plugin, right? Plugin file.
Wait. Okay, yeah, so this we close. Now you go to wait, you click it here, not wait. Click here, number 5, and then 299, yes, click. And you load. Yeah, load it. 5, 299. Good. Download. Well, let's go here. TrackMate 5. Now, 599. Maybe quick access. If you download it. 299. Yes, click. Yes. Click. Load. Good. Okay. Okay, yeah, I think we're good.
Okay, I continue?
Yeah.
Okay. So let's continue with this file, right? So now these are the trajectories. The first menu we want to look at is the display options menu. So it's around the middle of the menus, right? The button, display options button. So this opens a large window, right? And here we can choose at the top of the window, we can choose what we want to display. So here the trajectories by default are selected, right? If I unselect it, not everything disappears. We can choose to display density map, right? We can display diffusion map or the drift map.
Okay, but here, this is what I showed you. So it does calculate automatically all of these quantities. Okay.
Right, and then now there are also options. So for each of these categories, there are options. So for the trajectory, we can choose the color. So we can use uniform color code or based on instantaneous velocity, as David have shown you. We'll come back to it later, right? But just by default, random color gives one color for each trajectory, right? Randomly one color for each. So these are not very, very important options, but now if we go to the density map, the options are more interesting. So here it's the density map options part of the menu. We can change the bin size, right? So if we want less resolution, I can put a bigger bin. If we want more resolution, I can put a smaller bin, right? Here I'm at 50 nanometer. You can see here I have more resolution. And when you will display a map, you will get a color bar that appears at the bottom left of the window, right? And you see here the minimum value is 0 and the maximum is 56,000. And actually, with density map, we have big variations. When you have bins with a lot of points, the density will be very large. So to reduce this variation and see it better, usually we use the log of the density map. So if you check log density in the options, this will just compute the log of the value. And you see that now the map is between 0 and 11. And here we have a better idea of the variations. All right, and finally, the last option we have is if we want to apply a filter on the map. So let's say, for example, I go even lower in terms of bin size, so 0.03. Now I have a lot of noise, right? A lot of variance. And if I want to reconstruct something a bit smoother, I can apply a local average filter of size n by n. So there's multiple sizes I can choose, 3, 5, etc. So for example, if I do 3, now you see it computes a local filter. If I choose 5, right now the things will be smooth. Of course, when you do this local filter, it introduces artifacts, as you can see here, where it was 1 bin, now it's 5, 5, 5. But this can be interesting to just better visualize what happens in the data. All right, that's the density map. Now, if we go to the diffusion map, so the diffusion map, again, it's just a number every time in each bin. And we have, we can control again the bin size. So if we go to diffusion map options, so again, we can reduce or we can increase. Right, we can change the bin size, which controls the resolution. Now, the thing is that with the diffusion map, we are computing an average, as David presented it. So in order to have reasonable values, we want to remove the bins where there's not enough points. So for that, we have these other options, which is called diffusion min num PTS, right? And this is 5, so it will remove all the bins with less than 5 points. So where the average is computed on less than 5 points. We can put more, for example, 10, and here we get even less beans. We can put less, for example, 1, and here we get more. And you also see that things get more noisy now. So this parameter is quite important, right, to get like realistic results. Now, one thing we can do if we want to improve the resolution is to use the cosine filtering that David presented you. So when we do cosine filtering, we are going to decouple the grid, the square grid, from the computation. When we just use the square grid, we take all the displacements that start in each grid. So now the resolution and the computation, they are linked. When we use the cosine filtering, instead of looking for a bin at the displacements that fall into it, we are going to look at all the displacements that fall in a circle around the center of that bin. And the radius of this circle is controlled by the parameters that you have, cosine filter radius, right? So now I can have very, very small bins. What matters is what is the radius of my cosine filter. And to not have a big artifact, what we do is we apply a cosine weight function as a function of the distance to the bin. So if your displacement appears very far from the center of the bin, it will not contribute a lot to the final value. Right now, it's a weighted average and not just a normal. So if we do this, if we click on apply cosine filter, now, right, we have a much larger number of bins, right, that have data. Because this 5 now is computed over all the displacements that fall into a 200 nanometer radius circle around each center. And you see that now we have these weird sausages that appears, and these weird sausages, they are controlled by this cosine filter radius. So if I reduce the radius, I will reduce this sausage, the size of this. What matters here is that for this method to make sense, you need your radius to be larger than your bin width, right? If the size of your bins is larger than the size of your filter radius, and now we get a much smoother. Be careful with this option that if you specify very small bin value or very large filter radius, as I've just did, it might take quite some time. My computer is very good, so it's not a problem, but I don't know on your laptop what will happen. Okay, moving on to the last option, the last map. So now this is the drift. I can wait. I saw that in the note.
So you have one second. Yes. So you have this. So basically now you see that you can have a much refined, and then we can estimate actually how what's the resolution of this. And so now much higher resolution in terms of how the diffusion. Yeah. Okay. So you have it. Good. Okay.
Yeah, well, okay. One last thing before moving to the drift, maybe. If next to diffusion here on top, you have a button called hist, and if you click on it, right, it will display an histogram of all the values of the bins of your map. And for example, what might interest you for a real experiment is to see what's this average value. And here you see the average value is 1.2. micrometer squared per second. So that's, for example, the value you could report as your diffusion coefficient based on this method. You can do that with the density. It's not super useful. And you can do that with the trajectories. And when you do it on the trajectories, it shows you the histogram of the instantaneous velocity. So basically, it's just the displacement length. So how much you move between two successive points divided by your acquisition time. All right. Should I move to the drift?
Okay. Okay.
So the drift, basically, it's mostly the same thing. Just there is one option that's interesting. It's the one at the bottom, the size multiplier. Here, you see these arrows are massive. We cannot see anything. Size multiplier is just a coefficient that's applied to both components of the vector to reduce them. So for example, if I put 0.05, now my arrows are much smaller and I can actually see what happened. Right. Otherwise, everything is the same. You can control the size of the bin, the number of points you need to compute the drift. You can apply cosine filtering, and etc.
So each color corresponds to one direction. So we have 4 directions: up, down, east, and west. Okay, so for example, when you have the 4 colors converging to one point, this is an interesting point where you can have potentially this high density region. Okay, I think it's good, yeah.
Okay, cool. So yeah, if we can find an example of a region with converging arrows. Yeah, in this region, it's not the best region in the world, right? But you can kind of see that you have arrows converging into points.
Okay, so of course, now we have the algorithm that will do that for you. You don't have to scroll over all your images. That will be the next point.
Yes. So one last thing is before going to this is if you want to export the maps, so you can go to the export button in the main menu, and here you can either save the maps as SVG, so as vector images, or as CSV, so as a comma separated values, right? If you want to read the map and make your own histogram, right? Yes, you have the option. We'll come back to it later with the. Okay, now well detection. So this is a big menu. So that's how it goes. So here, the first thing is you need to give a name for your analysis because you can have multiple analyses saved in the plugin. So by default, it's analysis 0, 1, 2, etc. Okay. Now here you can specify what type of algorithm you want to use. And then you will have options related to the algorithm. So you can choose what type of estimator you want to use, what type of scoring. Okay, so David presented a bit the different algorithms. So basically this interface implements all of the algorithms. For the sake of just doing things quickly, we can say that as an example, we're just going to run directly the plugin now and just use just use these default parameters. They kind of make sense. They are not super optimized. So right now we are running the hybrid algorithm with the least square estimator for an elliptic boundary. And we are going to find the best ellipse based on the best parabolic score, which is derived from the least square error.
So just 1 second. So you remember I said there are different algorithms. So you can choose the algorithm. You can specify some parameter, but that the parameter by default. Okay, so do we need to change something here?
No, you can just run it directly.
Okay, so you run it, and we see the bar, blue bar is calculating. Okay, you see the two, yeah. Maybe we should, yeah. I mean, okay, let's wait.
Yeah, so once you press on compute, you will have this bar that will get filled more or less fast depending on your computer, and then you will have some results appearing in the.
Basically, run the algorithm, find the region of high density automatically, apply the algorithm, and at the end, the algorithm will give you a collection of circles where are the potential where, and it will give you all the statistics. We'll see in it comes.
Here in the console, right, it shows you how many wells it has found for each time window. So in the first one, we have 84 wells, in the second, we have 6. So yes, the computation is applied for each time window, independent. All right, on my side, it's done, so I can close this window. And now if I go to the main menu, I have my analysis 0 here. Num elements is the total number of wells, so 160. Here, if I click on show for the parameters, it will just open a window with all the parameters that I used in the algorithm, right? That's if you want to double check later. And now what's interesting is to click on view here in this checkbox. And this will do 2 things. This will open this table here, detected wells, and it will also display the wells on your trajectory, on top of your trajectory. What we can do to see them better is to go to display option and change the color code of the trajectory to uniform. Right now they are all yellow, and now we can see better where the
Okay, I think we are good. So if you want, you can also go to our here digits with just trajectories in one color. Then you have the potential value. Okay, this gives you. Then you can see if you're happy, not unhappy. Then we can change the parameters. But that's basically how it works. Okay.
So you can, yes, on the table you can click on a row, and it will highlight the well in magenta in your image. And on the other hand, you can click on a well in your image, and it will highlight it in the table.
Okay, that's clear. So you can go in one direction. You can click on the image and get in the table the information about the well. So maybe you should look at the table. On the table, you have the position X and Y, where is the center of the well. You have the axis A and B. You have there's a phi which I will discuss, which is how tilted is the ellipse, and then you have information about the diffusion coefficient and the energy, the score. The score gives you how good is your reconstruction. If it's close to 0, it's very good. If it's close to 1, it's very bad.
Yeah. Yeah, so as David said, right, on the table you have the frame. So the frame, this column here is where the well appears. So these are all in frame 0. And then you have other wells in frame 1. So right, in which time window. Then you have X, Y, this is just the position of the center. A, B are the length of the semi-axis of the boundary. Phi is the orientation of the boundary, so it's the angle of the ellipse. A and D are the attraction and diffusion coefficient of your wells. And A over D is the energy in KT. And the score is derived from the least square error in this. And also you have the residence time, as David mentioned. All right, finally, the last thing you have in the table is the family. So the family is just to follow wells in different time windows. So there was an option when we detected the wells that was called well linking. And basically what we say is we are going to consider that two wells that appear less than 100 nanometer apart in successive time windows will be in the same family. So basically, if you're in the same family, you're the same well in time. And there is an option in the menu, in display options. We can color code the wells by family. So if I click on it, you'll see that the color of the well change, and the wells from the same family will appear in the same color. For example, here I have a well, right? And the next frame, I have kind of what we can think the same one.
For those of you, wait, just 1 second. So I think, except you, Cecile, where you didn't click on this option, now you look at the time lapse. Okay?
Yeah.
Get this at a given time. You have a well, it's colored, and then you can go to the next frame in time to see if the well persisted. And that's how Pierre did this linking between the wells, so that you see how persistent they are. Here we didn't click on the option, that's why you didn't get it. It was at the beginning, that's why you here it was 1 second. You have the screen? No, you don't have. No, you don't. Nobody has it. Okay, you forgot to tick the time window.
Okay. It's fine. It's not a very big thing. One thing that
time, you have the next time to make sure that they are the same well. So you have to leave them. If for example the center is almost the same, but it can have some fluctuation. Right. What do you click for this? You click at the beginning when you download the image. Yeah.
But it's not an important thing, right?
Okay. Let's continue.
Yeah. So we're almost done for the wells. There are just two things. Is if you go on the detected well tables, at the bottom left, you have a button called Export Stats. If you click on it, it will save this table as CSV. So my wells.csv, right? And this is, where did I put it? Yeah, here, right? It's just CSV file. It's exactly the same thing, but in CSV.
So the idea is that you can export, if you want to extract statistics in MATLAB, Python, you can export this file, and it will allow you to get all statistics of interest. If you want to do the box plot, the Bayesian plot of the distribution of the different elements that how to do it.
Now, the second thing you can do is to directly export this image. So if we go to the export menu, and we have an analysis selected here, so I have my wells selected, I can choose to export the wells. But just exporting the wells alone is not really necessarily interesting, so I can choose to export also the trajectories. Right, so if we go and select Traj and wells, and now we can either save individual, so here we need to provide a folder, and if we choose save individual, what it does is export the trajectories on themselves and export the wells on themselves in two different images. And we have one image created for each time window, right? Exactly as you would have the main display. Now, what's more interesting is to do save overlay, and it will save everything on the same file. So now I have a file that's called overlay traj well. Right?
Yeah, why don't you open an overlay so people see what?
Yeah, I'm opening it.
So the idea is that if you want to make a picture of all of this, you will get, it can be exported, you can open it with Inkscape or whatever you want, and then you get this. So you can use this for making figures.
All right, that's the overlay. You got your scale bar somewhere. And so this you copy paste in your paper, and that's done, right? These are vectorial, so I can say, I don't like this trajectory, let me remove it, or whatever. All right. So that's the export, and that's, yeah, all there is to it for the wells. If you want David to show the graph now.
Okay, so 3 minutes of theory, and then we go back to the practice. So now let's go to this well reconstruction. Okay, so I explained to you the theory of how we can use all these single particle trajectory to reconstruct, this region of high density, the potential wells. Pierre showed you how to manipulate, so that all of this has been developed. I'll give you the reference later on of all of these different algorithms, the different works, so you can, if you're interested, look into it. So now I would like to finish with the application to trajectories that allows to reconstruct the topology of an organelle, such as the endoplasmic reticulum. We also applied, for example, at some point to mitochondria network organization. So, all right. So how do you reconstruct a graph? So of course, if you have SIM images, electron microscopy images, as we've seen yesterday, you get the classical view of the ER, it is the peripheric ER, where you have nodes that are connected to other nodes through three-way junctions. So this is what you see, but are the molecules inside exploring this uniformly or not? And can we use this ensemble of trajectories to reconstruct the structure? Because it's one thing to see, and the other thing is to see what is the reality. If you are in a city, you can see from the sky, from the satellite, that you have all streets available. But if for some reason there are workers, the street would be forbidden. Nobody will. So how do you see this? You need to see that there's a car or not, right? That's the same idea, same concept. So you get this ensemble of trajectory, and what we discovered a couple of years ago is that if you do the representation not as one color, one trajectory randomly chosen, but rather color code the trajectory according to the velocity. And what we discovered is that nodes were associated with a low velocity, and tubules were associated with a high velocity. And this was the idea, to use this to do the reconstruction. So you get a trajectory. We have looked together how you can reconstruct those potential wells. And this is a density map where you have the overlay. You can do the diffusion map. And then how do you reconstruct a graph that will represent the underlying structure so that you can, for example, calculate, as you mentioned before, you know, do you have, for example, for a given amount of time, the same amount of trajectory that goes from left to right or right to left between two nodes? And actually what we found out is that you can have, for some time, a notion of bidirectionality, that is almost the same trajectory that goes, but not necessarily in all nodes. Sometimes you have trajectories flowing in only one direction, and we call them unidirectional. So you can do this for the allotag ER to see the structure. So we tried different cells, and it was working in all cases. We could see that this density map with this separation between high density region versus the tubule. So this is to echo what Lippincott-Schwarz said yesterday, that probably at these three-way junctions, you have mechanisms of accumulation. So she suggested you have the lysosome interaction and protein expression through this messenger RNA. So this, we published that 2018, was much before what she presented, but it's still unclear why you have an accumulation of luminal protein in those structures. What's the mechanism? So we don't know, we just characterize them. So this is what you see if you look at a membrane protein, and nothing happened like this. It's very different. There is no structure in potential web. So motion on the membrane, that's what we discovered at that time, is very different from motion inside in the lumen. Okay, so how would you reconstruct? What's the strategy? You draw a line that would be a threshold. What you have below this line would be low velocity. You look at the trajectory that are characterized by this, and this will give you your region of low velocity, which are associated to the nodes. So this will allow to reconstruct nodes of a graph. On the other hand, if you look at region of high density, this will be your tubule, and this will allow you to connect those nodes by these edges. And then you get your entire graph. You get the position of your node and the connectivity. Right? So, and that's what the algorithm is doing. You have the trajectory. You look at where are the region of low velocity, high velocity. You identify the region of low velocity according to an algorithm that will create these polygons here. Once you have these polygons, you can reconstruct with the region of high velocity, the connections, and that's give you here the edges between the nodes, and then you reconstruct your graph. Okay, and so in the end, you get this, and you can now, since you know where are the region, you can say starting from one node, what happened? Do you have between two nodes the same amount of trajectory during a certain time coming? I mean, exchanging or not? And so we started to look at this and put the notion of unidirectionality, bidirectionality. And if you take a threshold about 75%, we found out that about 90% of the network allows bidirectionality, and a few of them allows only for unidirectionalities. And then you can take a specific node, take all the time that you have, and start to ask the question, how many nodes it is connected to, and in average we get 296. But in average, the what is called the index of connectivity is 3. You can look at in average the fraction of outward trajectories, and you can see that the fraction is about 0.5. So in average, you have the same fraction between going in and out. Okay, so those are the references before I leave Pierre the next 5 minutes that remains. Those are the references. So all the algorithm has been presented last year in the cell report methods. So if you're interested, we have all the algorithm described. We're actually writing a review now, where we're going to summarize what we've been developing in the last 5-7 years. So this algorithm, this was applied. So what we did with Pierre on the ER. All of the other work on calcium voltage channels appeared this year. The reconstruction of the trajectory of lysosome from the reconstruction of the trajectory and the discovery that is associated to the ER appeared a couple of years ago. The work we did with Pierre, the first part was published in this paper where we describe for 2 examples, phospholipid and voltage calcium channels, the first algorithm where there was no hybrid version. And then many years ago, with the first review, the idea is how you combine these trajectories together to extract information. So there are 2 reviews. Okay, so I will end here. And now I will leave Pierre showing how you apply this algorithm to reconstruct this network, and that will be the end. Okay, Pierre, I think you can share.
Yeah. It's okay.
Yeah.
Okay, cool. So last menu, graph reconstruction, graph construction. So as before, right, you have the name of the analysis, so it will also appear in the main menu. Now, basically, for the reconstruction, you have 4 main parameters. The first one is your velocity threshold for determining what are low velocity regions versus high velocity regions. And the other parameters are related to the scan, and the last parameters is related to the shape of the node, so either polygon or ellipse. To determine this velocity threshold is very important because it will really be a main parameters of the method. So to determine what you should put here, a good thing is to go to the display options and color code your trajectory by instantaneous velocity. Right, so now you can see what David told you earlier. You have this blue region separated by orange and red. Now what we can do also is use this option to filter out trajectories with more than a certain velocity. For example, if I put 10 here, I end up with only the displacements that jump, that have a velocity less than 10 microns per second. If I do 7, if I do 5, right? And the idea is to play with this value to try to find where you start seeing this accumulation rate. For example, 7 is okay. So now in the graph detection, I can say, okay, my velocity threshold will be 7. The 2 dB scan parameter, you need to play a bit with them, right, to find what's the best. I did it before, and I found that if I choose R equals 0.1 and N equals 10, it's fine. And the node shape, you don't really care, polygon or ellipses. So if I just go back to my trajectories, for the trajectories, okay, and now I do compute. Now it's going to compute the graph for each time window. Done, and as before, you can see that analysis 1 is here. I can see the parameters, and now I can also see the graph.
Yeah. We have a question, is that how do you go back from the instantaneous velocity? How do you know at which position, what is the instantaneous velocity? Can you click on something?
Instantaneous velocity here?
Yeah. So for example, now I want to go on the figure on the image, and I would like to, yeah. So for example, yeah, exactly. You choose a region. What is the velocity of a given region?
No, you cannot know what's the velocity of a region. What you can do is remove displacements that are faster than a threshold that you specify.
Okay, so you cannot do that at the moment.
How can you define a threshold?
You can look at your distribution because you have your histogram of distribution. That's what you did the first part of the.
Yes. So when we set a threshold in the interface, right, it's basically we remove everything that's above 5 in this histogram, right, and we keep only the things that.
Yeah, you don't have the delta X distribution for the grid.
No, I do not do it.
Because if you want to select the threshold, it could have been good to have this distribution of velocity so that you can decide yourself, no? Otherwise, how do you?
On the drift map.
Yeah. Yes.
Yeah. We never did it this way, but
I'm sorry.
Yeah. I mean, it's just we never did it this way, but yeah, we could.
I see. But because otherwise, suppose you start with your data, how would you define the threshold? If you need to have some statistics of the delta X, no?
Yeah, but the statistics of the displacements, you can see them in here, right?
Okay. So this is the statistics. Okay, but this is in a micrometer, right?
Yeah, in micrometer per second. This is the displacement.
Okay, so you have it.
Yeah, for the displacement, not for the drift.
Okay. Voilà, c'est ça. Voilà. So you have it. Okay. Okay. So you have it.
Yeah.
Yes. And then you have it. So you know what is the distribution, so you can decide your threshold. Okay. So let's finish because I have to leave soon.
Yeah, okay. So there's just one more thing, right?
Oh, you got this?
No.
So wait, so you did calculate? You have it? Yeah? Where is? Yeah, compute. Yeah, what, yeah, so you see. Yeah, okay. So you go to display option, so display option, put density. And so you see where they are, for example. So you can put trajectories in one color. Yeah, you put, yeah. No, that's one. So you see, this is not great, yeah, because you didn't change the parameter like here said in 0, 1. Yeah, 0 to 0, 1, 0, 1, and you apply it again, and it's not changing. Personne n'avait pas mis 0,2, et il y a un truc comme ça moche qui apparaît. Il n'a pas bien détecté. Okay. So, pareil, là, ah non, maintenant c'est bon. Everything's okay? I follow the okay. Okay, you want to say something else?
Yeah, that's just another option is, you see, for example, dbScan is great, but it's not super well adapted to SPT, because if you have regions that have different densities, it's not going to work well. It's going to create big nodes because dbScan wants a uniform density. So we have a way around that in another algorithm we developed, which is dbScan recursive. So what this thing will do is start by applying a dbScan, a normal dbScan, and now it will select all the nodes that have more than a certain number of points that you specify. So here it's 100, and it will try to divide them again. by applying another DB scan just on these points, but with a bit more stringent set of parameters, right? And it will do that recursively until all the clusters are below the threshold you specified, or it exhausts its parameter, right? So it's a simple application of multiple DB scans with your big cluster. We could run it, but okay, it's not super important.
So yeah, one more time. What do you need to change in the recursion?
What, sorry?
In the construction algorithm, in the induction several times of DB scan, what are the parameters you have to change?
In the recursive?
Yes.
So here I would do 7. Here I R min 0.1, R max 0.2 is good, and then this is that would be the parameter. So just change R min to 0.1 and like the mean core distance and the velocity threshold to 7. And this is a bit longer, so yeah. So yeah, there's one more thing I want to say generally, right, on the plugin is, so you've seen there's a lot of parameter optimization. It's not necessarily very convenient to do it by hand. So there's programming interface to this whole thing that you can access through Imaj, right? You can make Python scripts that's run in Imaj, and you can access all these functions through scripting, and you can run optimization or batch and everything. And that's the way I use the plugin mostly, right? And then from these scripts, you can save plugin files that you can then open in the interface and look what happens.
Okay. Thank you.
So we get your slide.
Yeah. Send me an email. I'll send it to you. Yeah, you can take it. It's you have a computer. Yeah, sure. Yeah, if an initial key, you just because I installed it on the computer, you can just get it, or you can send it to you by email. If you have a Gmail account, you can log in and send it to you. Okay. Send me an email and I'll send you the file.
So it's better that we continue discussing.
Yeah. So basically, now I would say that so this is the file that Pierre has developed that summarize this practical information that we did today. If you have data of this type, now you can use this plugin to really do cutting edge analysis, right? So it's new and very few people have used it so far. Okay. Yeah, if you sure, try it.
But it works only mostly for surface proteins.
And also for the ER, which is luminal.
Yeah, for every
in membrane and cytosolic, the lumen. Now, if it's 3D, then you have to have a way to get the 3D, but we don't we haven't implemented that here. Yeah. Okay. Good. Pierre, thank you very much.
Yeah. No problem.
And yeah, I'll talk to you later. Okay. Great. Thanks.
Bye.
Bye.
Thank you very much.